In the previous video, we learned about the partition function Q and got a sense for what it is. And now I'd like to move on to 13C where we can do some calculations using Q. And I'm just going to do a couple of examples of that now. So the first one I'd like to do is the mean energy, which is the mean energy per molecule. We can find that if we know the partition function. So let's say we have n molecules in our system, and the energies are given by a set of epsilon I. So each one of these n molecules has some energy for some value of I. And then I'm going to denote the total energy of all the n molecules added together with a capital E. So what is the average energy per molecule? Well, if we know the total energy and we know the number of molecules, we can just divide those to get the average energy per molecule. And E, we can calculate using these energies and also the population of each state. So energy state epsilon 0 has a population n0, epsilon 1 has a population n1, and so on. So if I want to calculate the total energy, let me put my 1 over n out here. The total energy is going to be the sum over all of the energy states of the energy of state I times the number of molecules that have that energy. So now we're going to use the Boltzmann distribution. And remember, the Boltzmann distribution gave us Ni over n. So I'm going to use it to solve, I'm going to solve that for Ni. So I need to multiply both sides by n. And the right-hand side was e to the minus beta epsilon I over q, the partition function. So the Boltzmann distribution was Ni over n equals this. So I'm going to plug that in right there. Okay, so my mean energy now is going to be 1 over n times the sum of epsilon I times Ni, which is this, n e to the minus beta epsilon I over q. And the n can come out because it does not depend on subscript I. Okay, so the n can come out, and when we pull that out, we can see that it cancels with the 1 over n. Likewise, we can bring q out because it does not depend on I. So we end up with something that looks like 1 over q times the sum of epsilon I e to the minus beta epsilon I. Okay, now I'm going to use a clever mathematical trick, which is notice what happens if I take the derivative with respect to beta. Okay, so this is why it's clever. We're using beta now as our differentiation variable. So if I take the derivative with respect to beta of this quantity here, e to the minus beta epsilon I, what do I get? Well, I'm going to pull down a negative epsilon I because of the chain rule, and otherwise this exponential will be left alone because that's the derivative of an exponential. Exponential is the exponential again. So I get a negative epsilon I times e to the minus beta epsilon I. And now if you compare this to this, you see that there's the same, but they're off by a minus sign. So I'm going to negate both sides. And so now I have the quantity that goes in here. And I can write it like this. So let's use that. So then minus sign comes out. And I have the sum over I of this. Okay, so I have the sum of a derivative. Well, the sum of a derivative is the derivative of a sum. So I can swap the order there. So I get negative 1 over q times the derivative with respect to beta of the sum over I, e to the minus beta epsilon I. And if you look at this quantity right here, we recognize this as the definition of Q. So this Q is going to cancel the 1 over Q. Oh, I'm sorry. No, it's not. It's inside of a derivative. So what I get is negative 1 over Q dq d beta. All right, so we ended up with this fairly compact form for calculating the mean energy. And notice it just depends on knowing the partition function. So this works when the ground state energy is 0. But what if it's not? What if the ground state energy is not 0? So if the ground state energy is not 0, then I think it's straightforward to see that I'm going to shift my average because I'm going to be adding some a constant to every term in my sum when I'm finding the average. And so this is just going to shift the mean up by whatever epsilon naught is. And so let's let epsilon naught, let's call it epsilon ground state. And so then the mean is going to be shifted by the energy of the ground state. So we wind up with this formula for the mean energy, the mean molecular energy. Notice here I have 1 over q times the derivative of q. So that reminds us of a natural log. When you take the derivative of a natural log, you get 1 over the argument times the derivative of the argument. So another way of writing this is by expressing this derivative as just the derivative with respect to beta of the natural log of q. Because when we take this derivative, we're going to get 1 over q times chain rule times the derivative of q. Okay, so this is the same formula. It's written in a slightly different form. So this is pretty cool. If we know q, that's all we need to know to calculate the mean energy. So I'm going to do an example using the two-state system again. And remember that two-state system was that the ground state, E naught, or EGS, epsilon GS, is 0, and epsilon 1 was some energy epsilon. And we already calculated Q, the partition function for this system. It's very straightforward since we know that there's only 2 energy levels, and we know what we know that they are 0 and epsilon. So Q then is just 1, which is e to the 0, plus e to the minus beta E1 with epsilon 1, which is just epsilon. Okay, so this is our Q for this two-state system. All right, the ground state energy is 0 up here. So actually, I'm gonna go ahead and use this form. The ground state energy is 0. So now I can plug in Q here and get a formula for the average energy. So let's do that. So now the average energy is the ground state energy, which is 0 minus 1 over Q. Here's my Q. Times the derivative with respect to beta of Q, which is, again, this. All right, let's calculate this derivative. So the derivative of the 1 is just 0. And the derivative of this term with respect to beta is going to pull down a negative epsilon. So I'm going to get negative epsilon e to the minus beta epsilon. And we see that the negative signs are going to cancel here. And now I'm going to simplify this a little bit, I'm going to multiply by e to the beta epsilon over e to the beta epsilon. Okay, so I'm just multiplying by 1. And you see what happens in the numerator here. This e to the minus beta epsilon times e to the beta epsilon, that's going to become 1. So the numerator becomes epsilon. And the denominator, the same thing. I'm going to get a 1 when I multiply this over here, plus 1 times this. So it's going to be e to the beta epsilon plus 1. And there's our formula for the mean energy of our two-state system. All right, so let's take a look at the extremes. If we take the temperature, the limit of the temperature to 0 and to infinity. So as t approaches 0, beta is going to approach infinity because it's 1 over kt. And if beta approaches infinity, then this average energy is going to approach 0 because the denominator is becoming infinitely large. And this is the exact behavior that we would expect, because the average energy is 0 because all of the molecules are in the ground state when the temperature goes to 0. How about when t goes to infinity? Well, in that case, beta goes to 0. And if beta goes to 0, this becomes 1 plus 1 in the denominator, so the average is epsilon over 2, which again is exactly what we would expect, because we have two states. One is energy 0, one is energy epsilon, and we saw before as t becomes really large, goes to infinity, the states are equally populated. So we'll have the same number of states with energy epsilon and the same number of states with the energy 0, and so the average energy is going to be 1/2 epsilon. Okay, so that's about all I'm going to do as far as calculating with the partition function for now. I'll just mention that starting from the partition function, we can also show that the average energy is equal to the degrees of freedom over 2 kt, which, remember, this is the equipartition theorem, which we were utilizing back in chapter 2 or 3. So we can actually prove this now just using the partition function. And if you want to see the details are in section 13C.2 of your textbook.